Hello, everybody, and welcome to this short session on challenges associated with condensate flow measurement, specifically in the context of steam use in process industry. So we'll just jump right into the discussion here. Uh, if you look at the process industry in general, the industry has very specific requirements in terms of how they want to utilize steam in process heating. Okay, and we'll briefly discuss that, but we'll also specifically talk about the condensate flow measurement part and the specific challenges associated with that. So, if we look at the process industry as a whole, what the industry specifically needs can be summed up using this particular diagram, using this particular schematic in a way. Okay. So if you look at this particular condition, you have steam coming in through a steam distribution header or steam distribution line, from which that particular steam comes in to this process heat exchanger. So the kettle part that it mentions, this is the process heating equipment. All right. So this is where the heating happens. And in terms of different process industries, the kettle may be replaced with some other equipment. But in most cases, this is just a representation of some heat exchanger, which is utilized in the context of providing heat to a specific process. And we'll take a couple of brief examples also of that particular aspect. Now, if we know this from a perspective of fundamental understanding, what the process industry really needs is thermal energy supply for process heating, uh, and there are specific criteria for it. The heating rate needs to be specific. It needs to be something that your heat exchanger is designed for. It can accommodate, and it wouldn't either overheat or starve the process in terms of heating rate. So starving usually results in a very long batch time. Overheating can result in damage to the product quality and so on and so forth. So the heating has to be at a required rate. It also has to be at a specific temperature. So just to give you an example, if we look at dairy industry, pasteurization is a process that requires steam in the background somewhere. And that steam is supposed to provide heat at a specific temperature to this particular fluid, the milk in this context. And the temperature can't be too low, otherwise the pasteurization itself will be ineffective. It won't kill all the pathogens, which is what the process is intended for. And it can be too high, which will otherwise spoil the quality of the milk. So it has to be a desired and specific temperature. It also needs to do this uniformly. So as I was saying earlier, if this is your steam line, if this is your steam tapping, you have pressure reducing valve, you have a temperature control valve in this context. You also have a pressure measurement gauge, a pressure gauge basically, where the heating is happening through this jacketed segment. All right. And if steam is entering into this segment, depending on what pressure is, steam will have a saturation temperature because it is a two-phase system. You have a specific pressure. With respect to that, you will have a specific temperature. But that temperature will be maintained uniform throughout the system. That's key to understand. So the heating has to be at a specific uniform temperature everywhere. So it can't be, for example, 120 degrees Celsius in this corner, 130 in this corner, and 90 in this corner. You know, it, it can't really have those many variations. It has to maintain it uniformly throughout. It also has to have flexibility because there are a lot of cases where the same heat exchanger is used for multiple purposes. So there you have to have a situation such that In one process cycle, you may require a higher temperature, in another, you will require a lower temperature, and so on and so forth. So that flexibility needs to come from the supply heat. In this case, it will be steam. And finally, it needs to be done at a reasonable cost. The cost optimization also is a part of this exercise. But what specifically concerns us this is the operation of this. Okay, so if we look at different industries, for example, you're looking at pharmaceuticals, chemicals, food and beverages, sugar, paper, textiles, dairy industry, which we just talked about. All of them will have a variation of this particular setup. Okay, and this setup may be different in different contexts as well. In some cases, there may be slightly more complexity in terms of the equipment involved and the steam line hookups involved. But in other cases, it may be a very simple system also to cater to all of these changes. So we'll just go through the overview of what steam does, its travel path, and the different conditions it has to accommodate. And with respect to that, what are the specific challenges we face in terms of the area of discussion for today, which is condensate flow measurement. So here, as we have already discussed, you've got your steam line, you have steam coming into the system. There is a pressure reduction valve, which will ensure that the pressure is within the safe limits. You can measure it or identify it through either a gauge or a pressure transmitter. There is a temperature control valve subsequently, which will actually modulate the flow of steam depending on what rate of heating you need. So if your rate of heating is lower, the valve will be throttled. It will be controlled. The opening will be closed to a certain extent, and the flow rate will be reduced. And correspondingly, you will get a reduction in steam flow rate and resulting in a reduction in heating rate as well. But the funny thing is, when steam enters into this jacket, the only amount of heat it can deliver to the process is the latent heat associated with phase change. So steam comes in as saturated steam, ideally, but in most cases, it will be some form of moisture contained within the steam flow. So very close to saturation, but still wet steam to a certain extent. And that wet steam will interact with this inner wall of this kettle in this specific case. And there, after giving the heat of condensation or heat of boiling or heat of phase change, however you want to put it, that particular steam is going to condense into water, which we call as condensate. Okay. And that condensate needs to be evacuated immediately. Because if we don't evacuate the condensate immediately, it will continue to pile up into this jacket. Now, while condensate will also have some amount of heat, the quantity of heat as well as the rate at which that heat is transferred are both very poor outside the phase change region. So if you have phase change happening, you have high quantity of heat also being transferred at a very high rate of heat exchange. But the moment it is a single phase system, whether that is superheated steam or single phase water in this particular case, subcooled liquid, what we call, in both of these cases, it is going to result into poor heat transfer. Okay. And if that condensate ends up getting backed up, again, you have differential temperatures in different segments, you have poor heat transfer rates, increased batch times, what have you. So that needs to be removed very effectively. And for that, we have what is known as a steam trap. The steam trap is a device which does exactly what the name suggests. It talks about it talks about trapping steam. So if steam is coming in, imagine a condition that steam has come into the system and there is no valve here. It is just connected to the outlet. Then whatever steam comes in, the same steam actually travels directly out to the exit without doing the heat exchange at all. All right. But if we don't allow this passage, then the condensed water or condensate will remain backed up. So what we essentially need is a specifically designed special purpose valve, which is what a trap is. So the trap will restrict steam flow going out of this particular line. But the moment you have liquid coming in, that liquid can actually go out of the system. So there is a specific principle of operation involved here. We won't do a deep dive. If needed, we'll share a video link of how this particular trap works for those who may be interested. So what happens is the float trap, or any other trap for that matter, in processes, it is typically the float trap. So the float trap will only allow liquid condensate to move out. This is at higher pressure, so the condensate can actually climb up a pipe. It is not a misrepresentation. So the flow trap can travel upwards. The condensate can travel upwards at the outlet of the flow trap. And once this is done, the rest of the process can continue. So the cycle will continue to repeat in this particular fashion. Now, what we want to discuss specifically today is how do we measure the flow of this condensate. So whatever condensate is being formed in this region or being collected in this region, being formed in the kettle or in the jacket, basically, of the process heat exchanger, how do we evacuate that is taken care of by the float trap, but how do we measure the quantity of it? That's the specific challenge we want to talk about. So this is one aspect of this. This is one thing we want to discuss before. Or this is we want to set the context in a way in terms of what we are dealing with. Now, traditionally, if we speak, if we look at understanding steam from the perspective of enthalpy and energy balance, we know for a fact that during phase change, there is a pressure temperature interdependence. So now what you see in front of the screen here is an extract of a steam table, some steam table, where you have temperature in one column and corresponding saturation pressure in another column. So this pressure is taken at saturated condition. It is measured in kilopascals absolute. So this is an absolute pressure value. Again, we won't do a deep dive into that specific aspect. You can Google this very easily, the difference between absolute and gauge pressure. And with respect to this, we know that if it is atmospheric pressure, like 101.42 kilopascals in this particular case, absolute pressure, the water will boil at 100 degrees Celsius because it is a pressure dependent phenomena, phase change. You know, so if you have a change in pressure, you will also have a change in a corresponding change in temperature for phase change. Okay. So as you increase the pressure of phase change, you also increase the corresponding temperature. Now that phase change can be boiling in the boiler or it can be condensation, as we just saw in the process heat exchanger. Okay. So it can be either of these two things. Now the challenge that we face is that for this particular condition, uh, the phase change can be different in different contexts. So we'll just take a small numerical example to set the stage in a way for our subsequent part where we talk about condensate flow measurement. Now imagine that you have a process. In that process, the steam is supplied at 140 degrees Celsius. Now, if we see 140 degrees Celsius, 140 degrees Celsius is about 3.6 bar absolute. You know, so as of now, just ignore this 5 bar value. This is just a variable essentially. But you have 3.6 bar pressure. The temperature of steam is 140 degrees Celsius. So what happens in this context, in this particular kettle, is that steam will condense at 140 degrees Celsius. So the saturated vapor or the wet vapor part will be at 140 degrees Celsius, and the condensate that forms that will also be at 140 degrees Celsius in a saturated liquid condition. So this is what they mean, that you have a saturated liquid at 140 degrees Celsius. Now you can do this with pressure also, but this is just a convenient way of representing it. So we are just going with a simpler option. So if you have a 140 degrees Celsius saturated liquid, that liquid is being throttled to 120 degrees Celsius. Now at 120 degrees Celsius, the pressure is about 1.98 bar. Okay, again, absolute pressure, which is equivalent to approximately 1 bar gauge pressure. Okay, approximately. So imagine a situation that for this particular process vessel, this pressure is 3.6 bar absolute or 2.6 bar gauge, and the outlet pressure is 1 bar gauge. Okay, 1 bar can come from this back pressure essentially. So the outlet has to overcome this much of a vertical rise in terms of the water column. So that can give rise to some pressure. There may be some equipment like a disc check valve or something. The pipe length itself could be longer. There may be bends, etc., etc., which will provide some form of a back pressure. Not only that, even this condensate return line, this blue header that you see, this could also have some back pressure because the line travels considerable distances sometimes. So this particular value represents the 120 degrees Celsius or 2 bar absolute 1 bar gauge, represents this back pressure, such that if you look at the operation of the trap in this case, the inlet is at 3.6 bar absolute, 2.6 bar gauge, and the outlet is at 1 bar gauge. So there is a pressure drop happening across the float trap. But the funny thing is, the float trap is not an energy conversion device. It is essentially just a throttling device. So that is what it means by the process being throttling. So in this particular case, the flow trap doesn't really do anything with the energy. It just redistributes it from high pressure to low pressure. There is no active ingredient here. There is no fuel being burned. There is no shaft coming out of the float trap, which will turn a turbine, nothing like that. So the end result is you get essentially an isenthalpic reaction. All right, so we'll talk about that specifically. But the second point is, because this is saturated liquid coming out at 140 degrees Celsius, that means the dryness fraction at 140 degrees Celsius is also going to be zero. Again, those of you who may not know what dryness fraction is, you can learn about this more. You can Google this. You can go to Marshall Bodhi tree, where this particular topic is extensively covered. But the dryness fraction is essentially zero because there is no steam associated with saturated liquid. It's just saturated liquid. So under this condition, you have a throttling process, which is essentially isenthalpic, which ensures that your inlet enthalpy and outlet enthalpy is same. So the enthalpy at this point and the enthalpy at this point is same, but their pressures are different. Corresponding to pressure, their temperatures are different. And corresponding to those pressure and temperature conditions, the enthalpy associated with different phases is also different. So if I have to plot, or if we have to plot a particular equation in this case, excuse me, if we have to plot a particular equation in this case, that governing equation is this. So you have the inlet enthalpy at 140 degrees Celsius and the outlet enthalpy at 120 degrees Celsius. These two quantities will become equal. Now we know for a fact that the dryness fraction at 140 degrees Celsius is zero. So this particular value will end up being zero. But the other parameters we will have to come out with respect to the steam table. So you have HF and HFG parameters. So HF you can find from this column, HFG you can find from this column, corresponding to 140 degrees Celsius. So this is your 140 degrees Celsius line. This is HF, this is HFG. As simple as that. Okay. So corresponding to that, what you have is that value you can get from the steam table. Similarly, for 120 degrees Celsius, you can find the same values, HF and HFG, again in the steam tables. So if you substitute all of those values in this equation, the only unknown remains is X at 120 degrees Celsius. Okay. So this X value at 120 degrees Celsius can be conveniently calculated. So, sorry, there is a small typo here. This needs to be X at 120, not 140. This is 120. So for this particular condition, the dryness fraction becomes 3.87%. Now, please understand what is happening here. If you look at this as a process, in that particular process, from inlet to outlet, the inlet was saturated liquid and the outlet has a certain dryness fraction. That means some quantity of that saturated liquid earlier converted to some quantity of steam, approximately 4%. So that 4% is now steam. And that is happening because the enthalpy associated with 140 degrees Celsius liquid is much higher than what the liquid itself can accommodate at 120 degrees Celsius. So that extra energy for maintaining energy balance has to convert to vapor. And this is the quantity of vapor that achieves this specific energy balance. Okay. Now, this is just an example. And in industry, you will find many examples like this, where you will have some amount of vapor conversion like this, which we call flash steam. Okay. So here you will always get some quantity of flash steam coming out of the process. The problem is If I have any flow measurement system associated with condensate, associated with saturated liquid, every time there is a pressure drop like this, so here the pressure drop was from 3.6 bar absolute to about 2 bar absolute, or 1.6, 2.6 gauge to about 1 bar gauge. Every time you have a pressure drop, you're going to get a phase change reaction. Okay, which is just to achieve energy balance. This is just to achieve your overall enthalpy balance in the liquid and vapor phases. Now, that's a major challenge because traditionally, if we see, if we have a condition like this, which is happening at the trap condition or a trap position, that inlet is just liquid, saturated liquid, outlet is some vapor. If you use anything like a venturimeter, you're going to get the same phenomena. You know, so here you will have a condition in which you will have a condition in which the flow measurement using a venturimeter relies on both the Bernoulli's equation, which leads to a change in pressure corresponding to a change in kinetic energy through the Bernoulli's equation. Again, we won't do a deep dive here. I assume the audience is fairly well versed with respect to this equation. And that change in kinetic energy will lead to a change in velocity, both between inlet and outlet. And similarly, there is the second equation, which is continuity equation. Between these two equations, all the rest of the parameters can be identified either through geometry or through physical properties. But what happens in these equation, the Bernoulli's equation specifically, is that as flow accelerates through this convergent section, its velocity or kinetic head goes up, but its pressure reduces. So you get a drop in pressure in terms of point P2. Your P2 becomes lower than P1. And if you are very close to the saturation condition, as mentioned here, under that particular condition, you're going to end up with a amount of liquid again converting to vapor. Okay. So here, if there is a pressure reading that you're getting, although the pressure principle will still remain the same, the flow principle now doesn't have a homogeneous flow. So if you do it just for the case of water, where there is no phase change due to this transition, the Bernoulli's equation together with the continuity equation will give you the flow rate. These two equations you can solve jointly in a way. So these are devices like venturimeters, orifice meters, pitot tubes, things like this. Okay. So this is there. This is something that is already existing in industry. But the moment you try to do this with respect to some a liquid which is very close to saturation, which is very close to phase change, every time you have this pressure reduction, you're also going to get a corresponding change in the phase, some segment of the liquid changing phase. So what it breaks is the homogeneity of the material. So the kinetic energy at the throat of this particular convergent section, or venturi if you want to call it, that uh, kinetic energy will be excessive because now it's not just liquid traveling, it's liquid plus some vapor. So vapor has a much larger volume, so the velocity increases drastically. And that change is not exactly positively captured due to this equation's non-homogeneity. So the rho part, the density part, is no longer constant. This is a challenge you face. So if I have to actually measure condensate flow at this condition, I can't have a section which changes cross section leading to a change in pressure due to a change in kinetic energy. If there is a pressure change, you'll always get a phase change reaction in this. So all of the conventionally available flow meters, like venturimeters or orifice meters, as we discussed, all of them are out. You'll always get some localized phase change, which will lead to an error. So now the question for us to answer is, how do we measure this particular flow rate? We want to understand that, sorry, there is just an error here. We just want to understand, how do we measure condensate flow? How do we measure condensate flow in this particular case at this particular location? That's the typical challenge associated with condensate flow measurement. I hope this gives you some kind of a context. Although we are not discussing the solution part here, This is just a conceptual engagement with respect to flow measurement, where you're specifically very close to the saturation curve. What happens in that particular context? That's what we are discussing here. So I hope this sets some context to you, and subsequent part we can discuss in another session, another discussion. Thank you.